To count the number of possible outcomes for a series of events, we can apply the fundamental counting principle, which says that we can multiply the number of outcomes of each individual event to end up with the total number of outcomes for that series of events. So if we think of dialing a phone number as a series of individual events where we're pressing a button, that's one event, then we're pressing the next button, that's another event, we can calculate using this counting principle a scenario like the one that's laid out here. So we want to know how many different 7-digit phone numbers are possible if they're to begin with a number other than 0 or 1 and can't have any repeats within the last 4 digits. So we can kind of set up a set of blanks here for us to fill in. So we've got 7 choices. I think I have one too many. So we've got 7 choices, and we have to determine how many options we have at each of those 7 choices, each of those digits. So we're going to start with a number other than 0 or 1. So if we think of the digits from 0 through 9, that leaves us with 8 possibilities for the first digit. And then for the next 2, we've got the full complement of 10. So 8 times 10 times 10 for those first 3 digits of the phone number. And then we can't have any repeats within the last 4. So that means for the first of those last 4 digits, we have the full complement of 0 through 9. But then whatever gets used here, I don't have available for the next digit. So that means I only have 9 options here. And then for the next choice, I can't use either of the 2 that I used in these 2 slots. So that means I only have 8 options. And then by the same pattern, we only have 7. Multiplying this out gives us a grand total of 4,032,000 possible phone numbers under these conditions. Now, when we're counting outcomes for a series of events like this, we need to consider whether both events will occur or whether one event or the other will occur. Beyond that, if both events are going to occur, then we need to determine if the outcome of one event will affect the other. So in the case of the phone number example that we just went through, there were some circumstances where what happened before didn't affect us. So we had the full complement of digits available for the second and third numbers. Didn't matter what we picked before for our next choice. On the other hand, for these 3, we had a restricted number of options depending on what came before it. So sometimes events are independent, at other times they are dependent. So that's the difference between whether past results affect future outcomes or if they don't. So we want to determine in these 3 examples whether the events described are independent or if they are dependent. You might want to take a moment to pause and consider that for yourself and then check to see your answers that I came up with. So in the first scenario, we have a summer camp and campers get to participate in a morning and then an afternoon activity. So the campers can choose an indoor activity for the morning and an outdoor activity for the afternoon. So in this circumstance, we're going to say that this is a set of independent events because we have these outdoor events, we have these indoor events. There shouldn't be any overlap between those. What we chose for the morning won't affect what we choose later. In the second example, it says because of rain, the campers need to choose a second indoor activity for the afternoon. This is another example where we're going to categorize this as being independent events. And the reason is we choose the indoor activity to start off the morning. There's no mention of any kind of restrictions that we couldn't do the exact same thing the second time in the afternoon. Maybe we played badminton in the morning, we could play badminton in the afternoon. Compare that against the last example where because of rain, campers need to choose a second different indoor activity. Now these events are dependent because whatever we chose for the morning is not available for us for the afternoon. So we have to read carefully through these types of examples to determine whether or not the events are independent or dependent. What came before it affects what happens next. Now in both cases, if we were actually trying to calculate how many possible outcomes there are, we would do the same thing. We would multiply the number of options for the morning times the number of options for the afternoon. The only difference is in dependent events, we have a little different notation here indicating that it's the number of outcomes for event B, but it's only after A has taken place. So in this last scenario, for example, If we have to choose a second different indoor activity, maybe there were 10 indoor activities, but now we only have 9 to choose from in that second round. Versus in this scenario here, if we had 10 indoor activities available to us, we still have the full complement of 10. So in both cases, we're still multiplying the number of possibilities at each stage of the process. It's just in the second stage of a dependent scenario, we end up with a different number as a result of that dependent condition. For some counting scenarios, we have some larger population, and then we're selecting some smaller subset of that population. And so we would like to have a shortcut as to how we calculate what the total number of ways we could pick that subset is. Now it depends on the rules of the situation whether we use a combination or a permutation to describe and then calculate that circumstance. And the difference is whether or not selecting that group of items in order matters or not. So in the case of a combination, we're taking from some large population a subset, but the order in which we pick those items doesn't matter. That all counts as the same. In other words, the same selected group of stuff in a different order does not count as something else. It is the same outcome. So let's see if we can see this in a couple of examples. So here it says that we're going to select 5 students from a class of 25 to be selected to leave class early. Got to feel sorry for these students since they're going to miss out on an extra 5 minutes of my greatness, but such is life. So in this circumstance, there's no indication that the order in which we pick these 5 students matters. So that means this is a combination. If I pick students A, B, C, D, and E, or if I pick them in the order E, D, C, B, and A, that would be considered the same outcome. So that means we're going to use a combination for that circumstance. And so in that case, we're going to set it up as 25 as our n, that's the general population, and then combinations, how many ways can we choose 5 students? And again, the order does not matter in this case, it's considered the same outcome. So I'm going to plug into this combinations formula. So I've got n factorial on the top, so I've got 25 factorial, can make that look like a 5, over n minus r, so 25 minus 5 is 20 factorial, and then r factorial in the bottom as well, so the 5 factorial. So we've got a lot of cross-canceling reducing that we can do. So if we expand this out, we've got 25 times 24 times 23 times 22. I'm not going to write them all out, don't worry. But from that 20, it keeps on going. On the bottom, we have 20, and then it keeps on going all the way down to 1. And then we also have this 5 times 4 times 3 times 2. And so the 20 factorial on the bottom with everything in the top from 20 on down cancels out. And then I still have this 5 times 4 times 3 times 2 that I can use to cancel out on the bottom as well. And so I've got 3 goes into 21 7 times. I can say 2 goes into 22 11 times. I've got 4 goes into 24 6 times. And 5 goes into 25 5 times. So in the end, I'm multiplying 5 times 6, don't overlook the 23, times 11 times 7. Multiplying that out, and we get a total of 53,130 different ways that we could select 5 students from a class of 25. Again, this is under the condition that the order in which we pick the students doesn't matter. Now take a look at the second scenario. In the second scenario, now we're saying the first person is going to leave 5 minutes early, the second is going to leave 4 minutes early, and so on. So we still have 25 students. We're selecting 5 students, but now whether you're picked first or last has an impact. It's no longer same stuff, different order is the same outcome. Now the order does matter. And so in this case, it is no longer a combination, but instead this is a permutation. Now, there is a formula for that, but in this circumstance, we could use the same counting principle approach that we had before, where for the first person, I've got 25 people to choose from. For the second, I have 24. For the third person, I've got 23 students left, times 22, times 21. And so if I multiply those out, we get a much larger answer of 6,375,600 different ways that we could pick the students from a group of 25. So the difference here is once we say that the order in which we pick the students matters, now we're talking about a permutation, which means we're going to have many more outcomes than we will if the order does not matter, where we see a much smaller number.